So, hi everyone, this is Yuyou. Today I want to introduce our most recent work, synthesizing practical transfer function in data flow analysis. And let's start. So first, let's do a quick recap on what is data flow analysis. So on the right, I give a simple LLVM IR example function, and data flow analysis tries to get information or properties that holds among all executions. So let's give a concrete example, known bits. So known bits is a information grabbed by the data flow analysis. It tries to determine if a certain bit is always 0 or 1 among all executions. So for a known bit, it can have three possibilities. If it's 0, it means that a certain bit in all executions are zeros. And if it's 1, that means a bit is always 1. Or it's unknown, it could be either. So with that definition, we can have see here. For the first operation, N3, it's a bitwise AND operation with arc0, which we have no idea about, and it's a constant 3. So we know after this AND operation, the first bits are zeros, and the last bit remains unknown, which means it contains 4 possible runtime values, 0, 1, 2, and 3. And similarly, for the next AND1 operation, the first 3 bits in known bits are zeros, and the last is 1, so we know it can contain 2 possible runtime values, 0 and 1. So this is known bits. And this is how LLVM implements that information in known bits. Yes, this is how LLVM implements the known bits. So LLVM implements known bits with 2 member variables, known zeros and known ones. So I attach 2 examples on the right. If a bit is always 0, then the corresponding bit in non-zero is set. Otherwise, we can look at the example at the bottom. If it's 1, then corresponding bit at a known one is set. If it's unknown, then no bit is set. So this is the known bits information. Now, since we know the known bits information on N3 and N1, how do we infer known bits on the XOR result? So in here, I attach the XOR truth table on known table on the right. By applying the truth table, we can know the XOR result. In LLVM, they implemented the truth table by a transfer function. So here, by passing the N3 and N1 known bits information to the function, the LLVM implements the truth table by executing the 3 lines of code, and we can get the result information and attach it to XOR. So in this example, the transfer function takes the known bits information on both operand, executed, and returns the known bits result. So this is a transfer function. And this is a simple transfer function on XOR. So LLVM also implements a transfer function for different operations on known bits domain, and some of them are really complicated. So this is an example about addition. So here I attached an example about the computer for add carry. It's a UTL function used by addition and subtraction. You see, it still receives 2 known bits operand, and it calls functions get min value, get max value, and a combination of bitwise operation and return the result. And well, at least it's not intuitive. So here's a summary. So known bits is just one domain provided in LLVM, and there are other domains like integer range or liveness information provided in LLVM and MLIR. And LLVM and MLIR implement the different transfer functions for different operations, defining a specification on all domains. So next, I'll explain why we need a synthesizer. So first, let me start with what our synthesizer can do. So in short, it reads a specification. Let's use the known bits as an example. The specification includes what is a known bits domain and the operation to be applied, for example, the XOR or add, and the signature of the transfer function, such as it receives 2 known bits information from both operand. And after the synthesizing, we can produce a result. We can give you some transfer functions. We can make sure it's correct. It always gives you the right information, and it at least return reasonable result. You can use it to do some optimization, people optimization, and it's in C++, which means you can directly include the result in your project and call it in your data flow analysis. So why do we need a synthesizer? So first, we can get more transfer functions, of course. So here I attach a table about different platforms and the number of intrinsic implemented with transfer functions and the total number of intrinsics. On x86 LLVM, at least I found publicly, they only implemented 30 intrinsics compared to total number of 17, 14 intrinsics. And for other platform, it's only 5 or 2. So by using the synthesizer, we can get more. And here is an example in MLIR. So in CompDelect, so CompDelect is a delect used in element circuit project. It only contains 7 transfer functions of operation compared to total number of 20 integer operations. And there is no known-bit analysis for RISC at all. So we believe other delects can get a benefit from the synthesizer, such as the WebAssembly, immediacy, and index. So we can get more transfer functions. And you might ask, so it's okay to don't have transfer functions. I can use those ones in LLVM. So let me explain what the difficulties in reusing existing ones. So first I'll tell you, yes, they did. So the example at the above is a known-bit transfer function they used in CompDelect. So if the incoming operation is a constant operation, the CompDelect directly reuse the LLVM known-bit structure. They make a constant function in known-bits and directly return the result. And the key question is, semantics might be different between 2 operations. So the first, I attach an example at the bottom, says the shifting operation in CompDelect. So it's totally okay if the shifting amount is larger or equal than the bit width in COM. So in that scenario, it's 0. So in this example, the shifting amount is 5 and the bit width is 4. However, it got problems in LLVM-IR. In LLVM-IR, it defines the shifting amount must be less than the bit width. In that result, here returns poison. So this is the first problem. And the second problem is here, in MLIR, there is another analysis called integer range analysis. It tries to determine if a certain variable always falls into a certain integer range by a lower bound and upper bound. So there's a file called infer integer range. It provides a set of util functions and shared by 2 analysis in arrays and index. So at the bottom example at the top, the bitwise AND operation in arrays, it directly calls the infer AND function in that util file. This is good. However, when it comes to index, it calls infer AND first. Then it calls to an adapter infer index operation to change the result to index domain. So which means programmers must manually write those adapters, and it might easy to get wrong, and it might contain bugs. So this is chicken difficulties. So the last benefit of our using synthesizer is we can prove the correctness of transfer functions. So to define correctness, let's bring 2 concepts here. The first is soundness. So soundness means the result must cover all runtime values. So here is an example about the run analysis result. So if our analysis result, so this run analysis result shows the only possible runtime value is 0, and of course it will lead to raw optimizations. So here is an explanation. Suppose the inner red circle is the set of all runtime values. We can include that set, it is sound. If it's smaller, it's a subset, or it only have a small intersection, that's unsound. The other property here is precision. So how many values that never occur at the runtime included by the analysis result. So the top result is 3 bit 0 and the last is unknown. This is the maximum precise result. So the second result here, of course, we can return 4 bits unknown. It also includes all possible runtime values, but it's not quite useful. So in this example, we say the first result is more precise than the second. So here's a diagram. So suppose we have A and B. A is a small subset at B, and both of them are sound. And in this example, we say A is more precise than B. So let's see how LLVM tests transfer functions. So this is code how LLVM tests transfer function. It first defines a bit width 4, and it exhaustively enumerates all possibilities of left-hand side known bits and right-hand side known bits and extra parameters. And also it enumerates all possible values in the first known bits and in the other known bits. So It takes a lot and it's not extendable to higher bit weights. And this is our previous work. So we can transfer. So if the operation and the transfer function are equipped with SMT semantics, we actually can turn it into an SMT query. So here we transfer known bits N3 and N1 into SMT expressions, and we call the transfer function lower to SMT, and we can got a result on SMT. Similarly, we have preconditions for all integers, they are included by N3. For all runtime 1, they are included by N1, and we perform the SMT version of XOR, and we check if all runtime XOR are included by the known bits without XOR. That's how we prove soundness using SMT solver. So it turns out we define a transfer dialect for transfer functions, and it encodes basic LLVM AP in the operation in SMT dialect. So for the top pass, we have transfer function in our transfer dialect that can be lowered to SMT dialect and become a query to Z3 for soundness. At the bottom, it can be lowered to C++, and we can compute its precision at a low bit weight. So I will attach a link below for our previous work. So in summary, our goal is not to beat LLVM transfer functions. I remember the first transfer function in known bits was 2007 or 2008 in value checking.C++, and then later it's split into a single known bits files. And people there spend almost 20 years to implement all kinds of transfer functions to improve the precision, find bugs. That's not our goal to beat them. Our goal is to provide sound and precise transfer functions in C++, so you can really use it for new operations or new domains. So next, I'll introduce the design of our synthesizer. So here is a big picture of our synthesizer. By reading the specification, we can generate a bunch of candidates, and we can evaluate the candidates. We add those sound candidates into our solution set. We keep pruning the solution set, and we generate the solution in C++. So this is a big picture. So now let's look at the specification. So the specification contains 3 components. The first is the definition of the domain, for example. It includes domain members, such as for known bits, it should include the known 0 and the known 1s. The next is domain constraint. For example, in known bits, a bit cannot be 0 and 1 at the same time in any runtime value. The last is constructors. So like say the default constructor of known bits is return all bits unknown, and the meet is given to known bits information. It returns the intersection of 2 known bits. And it also includes the definition of the operation. We assume the operation must be equipped with SMT semantics. In previous example, we can lower XOR or addition to SMT solvers. And the operation itself, it might contain some constraints, such as our previous example, the shifting operation. The shifting amount must be less than the bit weight. And lastly, the transfer function signatures, like say taking known bits from left-hand side, right-hand side, or other parameters. So after having the specification, we start with the function signature. We fill out the function with random operations, and we keep mutation the transfer functions step by step. So the reason we use random search is the search space is extremely large, and we cannot enumerate all possibilities. So here is a concrete example about what one-step mutation. I took a code snippet from our synthesizer result. You see here it contains autogen 9, 10, 11, and there are 2 possibilities. The first is we take a random operation, we change the operand. So in this example, in the top example, we replace the autogen bitwise AND operation to a multiplication. In the bottom example, we change the first operand from autogen 6 to autogen 9. So after finding possible candidates, so we should evaluate those candidates. And so this is our evaluation engine. From the bottom pass, give a candidate. We send to SMT solver, and if it's sound, we can add it into the solution set. Otherwise, we reject it. The other way is we can do a exhaustive testing in C++ at a low bit weight. Then we can get how precise or how good is this transfer function. If it's a sound, but it's with low precision, we still don't want that. So what candidates does the synthesizer keep? We save two kinds of candidates. Of course, the first one is it's a sound, and it's also has a high precision. We want it, so we keep it. The other is those candidates only sound conditionally, but still with high precision. So which means they only sound in a small area and must be got with preconditions. So this is what happened in the this kind of candidates. So instead of synthesizing the body, we're synthesizing a if precondition. If the precondition is true, or the God is true, and the return and we call the candidate body and return the result. So this is how we keep candidates. And the next is by keep adding the candidates into our solution set, and the solution set becomes larger, we want to remove those less effective ones. So here is how we use a greedy strategy. Suppose we start with the old solution set, and we evaluate the candidates based on the new solution set. Of course, the new solution set is empty first, and we select the one with most contribution. If the contribution is larger than 0, and we take it, add it to the solution set, and repeat this process. And if the candidate with most contribution is 0, which means the left candidates are useless, or they made no contributions, then we stop this process. So finally, we will end with a solution set with a set of candidates, and we generate a cycle plus. So this is how we generate a cycle plus. We merge all the result, and we merge the result from all candidates or partial solutions. So this is a synthesized result from XOR. It contains two candidates, or say two partial solutions, and we emit the result. Here is more complex example. For subtraction, it contains 16 sub-solutions, and it must be merged that amount of times to return the result. The reason why it works is for every, we make sure candidates are sound. So by merge all the results together, it's still sound because it must include the runtime values. So finally, here is our experiment result. So here is some partial result. We synthesized 39 operations on Gnome's domain on transfer functions. They are tested on random 8-bit inputs. So the table on the left is some transfer function. We did a good job. For bitwise operation and or XOR, we have the same precision as the LLVMs. And for enzyme mode operation, actually we achieve better. We have a 59% compared to 53. And for the enzyme shifting with the saturation, we have 97, while LLVM does not support this operation. And then for multiplication, we have 60. So the table on the right is some transfer function. We did a bad job. You can see here, average flow, we only have less than 40%. And for shifting, absolute difference. At the sub, we only have around 60% precision, while LLVM has nearly 100%. So I would say the results are very sensitive to random factors, such as the initial program and leading to variabilities between rounds. So this test we are collected on random 8-bit input, and we also did the evaluation on spec 2017 CPUs. So here we did at least say not a bad job here. Look at it. GCC, we compare the numbers found by LLVM and found by ours. We only have 1.78 precision loss, and we even achieved the same result as on MCF project. And among other projects, we have like 3, 4, 5% loss. And we also did some bad job at X264 and Lela. We believe they may contain a lot of instructions that our transfer function did a bad job. So this is a summary. So our goal is not to be the LLVM, but to generate correct and precise transfer functions when it comes to a new dialect or new domain or new operations. So by reading the specification and the operation equipped with estimated semantics, the synthesizer can generate usable and sound transfer functions used in data flow analysis. So this is the end of my presentation. Thanks for listening.
Right, questions?
Hey, thank you so much for the talk. I was hoping that you could just answer a really quick question about how long this synthesis process takes.
Well, so we have different parameters about the synthesis. So, like I said, there is a one-step mutation. You can have the configuration about how many steps you take and how many steps you collect the transfer function once. So, in our experiment, a synthesizer of transfer function takes like 1 or 2 hours. So, for 39 or 40 operations, it like takes 80 hours or even less.
And then also, could you just get some insight about the amount of time it would take a developer to write up the specification that's needed to perform the synthesis versus the amount of time that it would take to just write the transfer functions myself and then perform like some kind of exhaustive testing on it?
Well, I have to say back to exhaustive testing. So LLVM only tests the correctness on bit width 4. So in reality, in our synthesizer tool, we found a lot of cases that they are sound at the low bit width, like say 4 or 8, but actually they are unsound on a high bit width, 16 or 32. So which means if you when it comes to those high bit widths, the transfer function might produce wrong result. So that's a benefit we have. So the other benefit is if you're providing semantics, that's back to our previous talk, you can get other good tools as well. Apart from synthesizing transfer functions, you can get free rewriting tools, generating more lowerings. That's referred to Matthias yesterday's talk. And so we're trying to convince people starting writing semantics first. We can give you a lot of tools for free. Yeah.
Have you found a decent number of new transfer functions that don't exist in LLVM currently? Have you considered upstreaming them or had any luck with implementing them into the existing compiler?
Thanks for the question. Yes, we consider that, but then we realize the problem is because of the code are synthesized auto-generated. Like we can look at the example here. I think we do have an example about random here. For example, this AP int 9, 10, 11, they are auto-generated. You can see they're filled with this. They are not intuitive and not human readable, and I guess no one would maintain it. So I would say it depends. If the community wants to read the synthesizer result, of course we can synthesize it, but I would say it depends.
Are the generated transfer functions minimal in a sense, or are they usually like much longer than they need to be?
I would say it's much longer compared to human real ones because as you see here, here is an example about, for example, these subtractions. It includes 16 partial solutions, and each partial solution is like around 10 lines. And we also have the mid functions. And in LLVM implementation, it's only like 20 or 30 lines. So yeah.
Right. Thanks again to the speaker.